There are a number of different mathematical operations that can be performed on tensors. And in this video, we will look at those operations. The first operation we will consider is the tensor product. Given two different tensors, t and s, of type n1m1 and n2m2 respectively, their tensor product will be a type n1 plus n2, m1 plus m2 tensor. If we just look at the case when n1 and n2 are 0, so that we deal with 0m tensors, the product of t and s is a 0 m1 plus m2 tensor, so it will take m1 plus m2 vectors as its argument. So if we let the product ts act on vectors v1 through vm1 and w1 through wm2, we define this as t acting on the vectors v1 through vm1, and s acting on the vectors w1 through wm2. And we can extend this definition to also include nm tensors in a natural way. The second operation is multiplication by a scalar. Given a tensor t and a scalar k, we define this as the tensor acting on vectors v1 through vm as just being the scalar k multiplied by the tensor t acting on the vectors v1 through vm. Again, similar definitions apply for nm tensors. The third operation is a so-called contraction. Given an nm tensor t, the 1,1 contraction, which we will write c11 acting on t, will be a type n-1 m-1 tensor. As such, it will take as arguments a type 0 n-1 tensor s and result in a 0 m-1 tensor, which therefore takes m-1 vector arguments, v1 through vm-1. For notational purposes, we will here often denote the tensor product between t and s as t o times s. With this notation, we write the contraction c11 acting on t as t acting on the dual basis vector ea, tensor product with s, acting on the tangent basis vector ea in the first argument, and then v1 through vm-1. Note here that we have a sum over the index a, as it appears twice. This definition is going to be coordinate independent, even though we have the tangent and dual basis vectors here. In fact, these two could be any two sets of vectors, such that EB inner product with EA is equal to delta BA, and the definition would be the same. Note here that this is the 1,1 contraction, since we put the dual and tangent basis vectors in the first position of the arguments. If we instead wanted to make a contraction of any other indices, say the KL contraction, we would instead have to place these basis vectors in the kth and in the lth arguments.